Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with numbers 5, 6, and 7 in your Unit 7 homework over thermodynamics. So let's see, number 5, it says a bottle containing 9 kilograms of water at a temperature of 15 degrees centigrade is placed in a refrigerator where the temperature is kept at 4 degrees centigrade. How much heat is transferred from the water to cool it to 4 degrees centigrade? So I'll start this like I start just about everything with a picture. I've got some sort of bottle here of, of water. So filled with water here. Now, in this problem, the mass of the water given in the problem, and the question is about, reading it again here, let's see, number 5, how much heat is removed. So when this bottle is placed in an environment where the temperature is 4 degrees C, but the temperature of the water is 15C. Yours might be different. Mine says 15C. Now what's going to occur is we're going to get a heat transfer from the water to the environment. And when that occurs, the temperature of the water, this number will start going down. Now the relevant concept here is specific heat, and the equation basically for specific heat is the Q for heat is equal to mc delta T. So what this problem is asking for is this: how much heat has been removed? This is going to be the mass of the water that was given in the problem. Specific heat is the specific heat of water. That's 4186 joule per kilogram degrees centigrade. Then the delta T you get from these numbers here and here. Now, what I'm not quite sure of is whether they're looking for a plus or minus. The heat transfer is out. I would just try it with a positive value. And if it doesn't take it, put a negative number and see if that works, because I'm not sure numerically how the computer is set up. You know, whether this heat term is plus or minus, it just kind of depends on how you ask the question. You know, how much heat is transferred from the water? Well, that would be a positive value. Answering it that way. That should be enough with number 5. Consider that one done. Let's chat about number 6. All right. Iron is melted during the recycling process. How much heat must be transferred to each kilogram of iron to bring it to its melting point, from which is 1536 C from room temperature 20 C. So we got some sort of chunk of iron. Here's my picture here. Iron. And it says each kilogram, so I'm going to imagine that this is 1 kilogram. And the initial temperature is given in the problem. 20 degrees C. Yours might be the different value. And then what we're trying to figure out is how much heat or how much energy is it going to take to get the temperature to 1536 degrees C. All right, so the relevant concept here again is specific heat. Specific heat relates heat to temperature changes. So I'd start by writing out Q equals mc delta T. And the mass, you're going to use 1 kilogram. Specific heat is going to be the specific heat of iron. You're going to have to look that up. It will have units of joule per kilogram degrees centigrade. And then the delta T you're going to get from these numbers. I think that's probably, oh, nope, there's a part B. About how many cups of coffee could you make with this amount of energy? Where 1 cup equals 73,600 joules. So when you get this number, it's probably going to be a pretty big number. Then use the 1 cup equals 73,600 joules as a conversion factor. Take this number and multiply by 1 cup over 73,600 joules. Right, so you're going to take a number with units of joules, and then you're multiplying by this conversion factor. The joules will cancel, and you'll be left with cups, and that's how you answer 6B. Let's chat about number 7. All right, number 7, it says, a 0.09 kilogram lead bullet traveling at 238 meters per second strikes an armor plate and comes to stop. If all the bullet's energy is converted to heat that it alone absorbs, what's the change in temperature. So the idea here is that we have this hard wall and this bullet traveling at the wall. Now, the mass is given, the speed is given, and from these numbers you can calculate the kinetic energy of the bullet, 1/2 mv squared. You're going to get a number in joules. The bullet hits the wall and basically flattens. Now, I don't remember exactly what my videos about this stuff look like, but anytime you deform material like this, the temperature of the material will tend to go up. So what happens is that as the bullet deforms, the internal energy here goes up, and as a reflection of that, the temperature goes up. So what they're saying is to assume that this number gets converted to heat, increasing the temperature of the bullet. So because they're talking about a temperature change, the relevant concept is specific heat. So you want to start by writing out Q equals mc delta T. And whatever this number is in joules, you're going to take that number and place it here. Now that's because it says in the problem to assume all of the bullet's energy, that's all of this, is converted to heat. So they're basically saying all of this is going to go here. And then the mass of the bullet is given in the problem. The bullet is made of lead. You're going to have to look up the specific heat of lead, and then you're going to calculate the temperature change from that. So I think that should be enough to get number 7 done. Hope that this helps. I think I'll just end that video here and start another one. Have a great day.